Today I'm just going to talk about some new ideas that we have at UWA. So, this is our team, so it's joint effort between our team at UWA, and this is the sort of outline. I'm not sure how far I'll get through, but first I'm going to talk about some new ways to calculate some new Axion terms. You're going to see a talk by Anton, and I thought it was a great paper on using monopoles to get some more terms for Axions. We're going to look at AC and DC haloscopes, and then we're going to introduce a new type of haloscope, which we call an anyon cavity haloscope, which is sensitive to ultralight dark matter through the photon interaction. Then I'm going to talk about gravity waves and comparing dissimilar Axion haloscopes, and if I get some more time I will go on, but I probably won't. So when you calculate the sensitivity of the Axion, you're actually using Poynting theorem. So when you do a resonator and you work out complex Poynting theorem, you can come up with this general equation where you get, if you've got a surface which might be your cavity, the radiation out of the surface will always be zero, and then you're left with two terms, and one is the Axion power input, another is the cavity power dissipation. Usually we put the cavity power dissipation in by hand, but if you do it this way, which is a standard way in electrical engineering, you can do it in a systematic way. The interesting thing is when you look at the Axion power input, is this is an imaginary term, so the way that you convert into Axions is through the complex electric field, through the dissipation. And in the dissipating part of the cavity, it's the imaginary part of E which turns this into real, and therefore you get a 1 on Q factor. That's why our sensitivity to Axions in our scan rate is only proportional to Q and not Q squared like everything else, because we lose a factor of Q here. And when we're in that dissipative part of the cavity, E and B are in phase. When you're in a conductor, E and B are in phase. So that is an interesting point. And then if we go to Anton's and Andreas Ringwald's latest paper, I was interested in that because it gave some extra terms to the normal Axion couplings. There's two extra terms because of some magnetic charge. And the interesting thing, it brings in two vector potentials for one particle. So you can just use Poynting theorem again to calculate the sensitivities. You can take the Axion electrodynamic equations and you can get a more general form of the equation. And when you go through that and you look at it, if you have a constant DC background magnetic field like most haloscopes do, you can take this and you get an extra term. This extra term is a B dot B term, and if you look at the sensitivity, there was now 3 parameters, and this second parameter here is the AB term. There is no BB term. But if you look at this, this integrates to 0. If you calculate this in a constant field, so this is actually 0 in most haloscopes, but it isn't exactly 0, because if this is a magnetic field gradient, you're actually sensitive. And this is very similar to what Igor presented about scalar dark matter. It's actually a very similar term. It's this extra Axion term that's here in this Lagrangian. This term here is very similar to the dilaton scalar field term. And therefore, this is approximately true, not quite true, but approximately for some. So some experiments that test for this scalar dilaton will also test for this Axion term. So that's very interesting. That makes the scalar dilaton much more interesting to search for. Then now I'm going to talk about upconversion experiments, and there was a poster by Katrina in our group. We can look at our upconverting haloscopes, and we can see we've got sensitivity now to the ABB term. So now we're sensitive to this monopole term that comes from Anton and Andreas's work. And we have these overlap functions, and your sensitivity when you go through all this maths, you have these two sort of overlap functions, and one of them is the normal one, which is our normal GA gamma gamma, is with your B as a background, your magnetic field in your background field, and your readout mode is this term, and the other one is the other way around. Now your electric field is your background field, and your B field is your readout, and they come there. And we can do this for frequency as well, because in the upconversion, the haloscopes, you're sensitive to both frequency and power, and we can work out the frequency, and again, that's sensitive to both terms, and we can work out the signal-to-noise ratio, and they're very similar. They're in fact the same form, and it just depends the temperature. This is a noise temperature of your readout system, and this is the noise temperature of your amplifiers. So they're totally consistent. And the interesting thing about these upconversion haloscopes is that we're actually sensitive to this GABB term when the DC haloscopes are not. So when we look at our upconversion haloscope, we try to choose a mode. There's many. You can do, if you want, you need to get the modes close together, so you can look at the sensitive modes when they're close together, and we can see a pattern in there on which ones are sensitive, but we don't really want to use these ones amongst higher order modes, so we limit our choice. But we really want to use m equals 0, because if m is not equal 0, we have degenerate modes, and we don't know if spatially which one we're choosing, so we could choose one that's insensitive to the readout mode. So you really limit to m equals 0. We can calculate these analytically, and you see the overlap functions are very similar if we choose the monopole coupling, the monopole overlap function, and the GA gamma gamma overlap function, except for a ratio of frequencies here. And that's true here when we look at another class of different modes. So in our experiment, we can say that our GA gamma gamma overlap varies a bit, but our sensitive to the monopole is this, the monopole term for the Axion. So they're pretty much the same, but in the end, this is your sensitivity. It's proportional to this overlap function, because we can take this overlap function out, and we can put a ratio of frequencies here. And so this experiment puts limits on both these terms. So now we know how to put limits on these terms. I will get to the, and that's what we can do with these upconverting haloscopes. So now I want to talk about this new resonator that we just put on the archive, this paper, and we have it submitted. We were interested in looking at more complicated symmetries of cavity resonators. So there's this classical Mobius ring resonators, and it exhibits fermion to boson rotational symmetry. And if we go 180 degrees flip as we turn around, that is a fermion symmetry. And the boson has no chirality, so spin up and spin down is the same, but if it's not if you have the fermions type geometry where you have a handedness, a left-handedness or a right-handedness. So that's the difference. So fermions come in two chiralities called left and right, bosons do not. So this is like obeys the behavior of a fermion, and this a boson. So this is typically the boson. It can be a torus. The Mobius is like a fermion, but what we do is what we call anyon. And that means you can make your cross-section any sort of shape, and then you can, if we twist it back on itself, it will have finite angles, a set of discrete angles that will work at these different symmetries. So that's two P symmetries, P rotational and P reflection, and so rotation by 2 pi on P preserves the object. So the simplest one to do is the equilateral triangle, and so we do that, and when it goes back on itself, we have this relationship. So here we are. We made these cavities through 3D printing, and we worked out how to model them with a mesh. And there's this non-zero helicity where a mode with non-zero helicity has its own non-zero E dot B term. So the mode itself has a non-zero E dot B, and that's the imaginary part of that. And we can look at these different modes, and we predicted their frequencies for different twist angles, and this is simulation on the bottom, and this is measurement, S21, and they line up exactly, so we could model simulation, and we could create these microwave modes with non-zero helicity. So what's helicity? Well, helicity is used in optics. It comes from this zilch electromagnetism where this conservation relationship was discovered and wasn't really fully understood till more recently. There's this thing called zilch current, which is this conservation law. And so here, Helicity is a pseudoscalar and spin is a pseudovector. On reflection, handedness changes, but spin doesn't. So it's like a mirror symmetry. And people do this in optics. They create these helical types modes. This is optical vortex beams or polarized light. And they use it to do spectroscopy on chiral systems. So what happens is that the axion is actually a chiral object. So building one of these resonators, it automatically couples to the axion. So this is, if we want to explain this a bit further, when theta equals naught and we have an equilateral system where it could be square, it could be triangle, but the sides are the same, you pretty much have a degenerate T and TM mode. And as you twist it, you get a magnoelectric coupling between degenerate modes. So there's a magnetoelectric coupling without any material. That's what's going on. So the basis set of your vectors go from your normal TE, TM mode system to this EZ plus or minus BZ. So that hasn't been done in microwaves before, only in optics. So these resonators have a totally new property, which is a pure photonic magnetoelectric coupling between modes. And with the Mobius, you've got a lot more modes with near unity helicity, and they can be plus or minus. That's the handedness. So we can look at how these couple. It's a resonator, and we can use the same Poynting vector type theorem, this time add modulations to the fields and do some sums, and we get this signal to noise ratio here. And this time it's very similar, and it's only couples within the bandwidth, so it's only coupling to ultralight axion. So as you improve the Q, you don't improve outside the bandwidth, only inside. So it's a sort of complementary experiment from where you can do ultralight axions through the photon coupling. And if you compare to the dual mode, you'll see in the dual mode system, it's proportional to the geometric mean of the two Qs, and this is its own background field, so it's proportional to its own Q. And you can see it's very similar sort of formula, except it's good for ultralight axions. So, and it's also sensitive to this same monopole term that Anton and Andreas have come up with. So we can search for this, both these the sum of this in the ultralight coupling regime. Now, I've got 2 minutes, that's good. I can just slip in the gravity waves and miss the last stuff. So we saw this before, and this interested me because I used to work on gravity waves and resonant bar. I did my PhD on resonant bar detectors, and so I was very interested in this, this high frequency, and we saw how our haloscopes are sensitive to this through this current term. And the thing is, though, I'm in the middle of writing a paper, and it should be just a week or so where it gets on the archive, and it compares sensitivity of dissimilar photonic axion haloscopes in axion dark matter and high-frequency gravity waves. So usually our signal, we assume, is like this narrowband noise with effective Q factor of 10 to the minus 6. And I've looked at a few experiments, and I've taken how long they've integrated for and blah, blah, and looked at this and simulated what sort of sensitivity you get, and shaft here, Abra here, organ here, just doing axion cogenesis, and ADMX here, and it all came pretty much the same. But it's a very inexact way of comparing. It compares how well we've done in getting to GA gamma gamma, but it doesn't tell you about the instruments. So what they do in gravity waves, they show you the spectral, and when they're comparing instruments, they don't worry about what the signal is, because here we're worried about the signal, and that's what gives us these curves. They just show the spectral sensitivity of the instrument. So when we're comparing instruments, and not worrying about signals, we just look at the spectral strain. So I can do that too for axion detectors, and we can thus compare the spectral sensitivity through to LIGO. And there you go, that's what I did. And I'll just finish here, I guess, since I've got no minutes left, and take questions.
We do indeed have time for questions. There's one at the back, Jörg.
I'm wondering about your kind of turning, twisting cavities. So could you in principle make them just arbitrarily long if you just have the right...
Say that again, your mask is muffling you.
So if you have the right kind of spiraling length, could you make them infinitely long so that the electric field is always pointing parallel to the magnetic field where you want to have positive interference, and then kind of in the perpendicular direction when you would have negative interference, and then back to positive again?
I think that's what the Mobius one does, the one that goes back on itself. It's just, I'm not exactly sure what you're asking, but in this Mobius type structure, not only are the geometric factors larger, so you get a factor of 4 higher Q because you've got less boundary, you get, so we calculated if we had the great results of, if we had used the great superconductor of Fermilab, we could get 10 to the 13 Q with the geometric factor. It's sort of like an infinite system because it just goes round and around and around, right? And there's more modes have high helicity. Nearly every mode family has some form of high helicity. I'm not sure if that answers your question.
I think so.
Yeah.
Let me think about it.
Yeah.
Okay, next question over there. Yes, I find engineering companies often don't respond when I ask them to build something infinitely long.
Hello. So as a naive theorist, I look at this plot. I have no idea what's going on. So
Yes, I know.
Can you share some words of wisdom?
I can share some words of wisdom, yes. So what we have here is this frequency of the mode. This is it's a Mobius strip, and this field pattern shows you the electric field in the twisted structure. And so this is just a triangular, this has got a triangular cross section, it twists around on itself, and these are all the modes in the structure and what their helicity, with high helicity. So it's like a mode map.
Okay, one more question
Thank
before
you.
coffee.
Thanks for your talk. Magnetic fields can also have helicity. Does that cause any sort of complication if your magnetic field has a little bit of non-zero net helicity?
I'm not sure. Well, this is quite simple. If I take no twist, let's take on no twist. If I've got an equilateral triangle, right, then I have degenerate modes that are TE and TM. As soon as I stop making that equilateral, they shift apart and the helicities are not as good. Equilateral is really important because you have to have degenerate TE and TM modes for this to work. As you twist it, the TE and TM modes couple together and the basis set changes. It changes from them being individual to being plus or minus, which is plus helicity and minus helicity. And so what you get is one tunes one way and one tunes the other way as you change that twist angle. So I don't know if that answers your question, but that's what happens.
Thanks.
All right, let's thank Mike again and then go to coffee.